Chemical reactions happen all around us every day. In fact, if it weren't for chemical reactions, life as we know it wouldn't be able to exist. That's what's up next on PS100. There are two key factors to understanding chemical bonds: entropy and energy. Entropy, as we discussed in a previous episode, is a measure of disorder. Since the overall entropy of the universe must always increase, reactions that are high in the increase of entropy can happen easily. Reactions can also happen easily if the materials involved are going from a high energy state to a lower energy level. But if a reaction goes to a higher energy level than it started at, it needs energy from an outside source. When you mix barium hydroxide octahydrate with ammonium chloride, they clump up and form a liquid slurry. Since this reaction requires energy, it'll take energy from the water touching the flask, freezing it. So, by looking at changes in entropy and energy, we can figure out whether or not materials will react. But how do we figure out how long that reaction will take? To answer that, let's take a look at strawberries. The sugar inside strawberries likes to react with oxygen in the air because that reaction results in less ordered products: carbon dioxide, water, and heat, increasing entropy. It also results in a lower energy level. As you've probably seen, this process can take a while. However, adding heat to the mix can speed this process up significantly. Your body is typically at 98.6 degrees, so it can undergo this process in just a few hours. But it can happen even faster. Add a strawberry to some molten potassium chlorate, and you get a fast and violent chemical reaction. So why does heat matter? Well, the rate of the collisions of the reactant's molecules plays a big role in the rate of a reaction. How fast molecules collide tends to be determined by their speed and the concentration of the reactants. The strawberry reacted much faster in the liquid chlorate because the oxygen atoms were moving much faster in the hot chlorate than they were in the air. But they were also at a higher concentration, which sped up the reaction even more. Collision rates aren't the only factor at play. Many reactions must get enough energy to reach what is known as the transition state before a reaction can begin. For example, there are sometimes bonds that need to be broken before a reaction can take place, and a certain amount of energy, known as activation energy, is required to do that. Until this amount of energy is reached, a reaction cannot happen. Entropy also plays an important role in reaction rates. In the same way that a key can only go into a keyhole one way, some molecules have to hit each other in just the right way in order to react. In these instances, there is an activation entropy required to get the molecules of the reactants oriented correctly. There are also molecules called catalysts that can speed up reactions but aren't used up in the process. They do this by lowering the activation energy or by helping the reacting molecules orient properly, which makes the activation entropy more favorable. Sometimes they do both. Because they aren't consumed when helping other molecules react, they can be used over and over again. Another reason the strawberry in your stomach reacts so much faster than it does when it's left out is because of catalysts in your stomach called enzymes. Without enzymes, chemical reactions wouldn't happen quickly enough to support life. You could increase temperatures, but that would speed up the reactions of decomposition in your body too. So catalysts can help speed up only the particular processes that utilize molecules of a certain shape and size. That's it for this episode. A big shout out to Dr. Henry Eyring. His famous work in chemistry helped establish potential energy surfaces as a way of understanding chemical reactions. And he's the father of President Henry B. Eyring. Thanks for watching, and as always, there's more science and research opportunities for BYU undergrads in the description below.